Hello again. In this video we're going to show how to graph simple exponential functions, what their parts mean, and also include domain and range. First thing we want to talk about is what is an exponential function? Well, it's a function that's in the form of y equals a times b to the x, or f of x equals a times b to the x. What makes it exponential is that your variable x is the exponent itself. Now we do have a few key features here, and that is a cannot equal 0 because the whole thing will equal 0. We're going to assume that b is greater than 0, meaning you can't have any negative numbers for your base value. And we don't want b to equal 1 because if we just have 1 to the exponent, we're always going to get 1 as an answer, 1 times a. Another thing I might want to point out here is that your letter a is almost considered your starting value. So your starting value is typically a 1, however it could be any number bigger than 1. We'll see that when we get to the graphs. Here we have a exponential function. Now I could write it like this here, 1 times 2 to the x, or I could put the 2 to the x in parentheses like this, or I could just leave the 1 off altogether since the beginning value or a value is 1. However, we do need to have something to indicate here that 1 is separate from the 2, so it doesn't look like 12 to the second power, and that's also why we put the parentheses on this one. So I've got a table of values here, and what we want to do is fill them out and then go graph them and see what it looks like. So we're going to start with the 0 because that's an easy one. So if we put 0 in place of x, we get 2 to the 0 power. Well, if you know your rules of exponents, anything to the 0 power is 1. If we put a 1 in place of x, so we have 2 to the first power, we end up with a 2. If we put a 2 in place of x, we get 2 to the second power, which is 4. And if we put a 3 in there, we get 2 to the third power, which is 8. Now that's the right-hand side of our graph. Now we go to our left-hand side, we have some negative exponents. So 2 to the negative 1 is really the reciprocal of 2 to the positive 1, so what we get is 1/2. And 2 to the negative 2 power is going to give us the reciprocal of 2 to the positive 2 power, which is 1/4. And our next step is simply just go graph these on our coordinate plane. Okay, so here you can see we have the function 1 times 2 to the x graphed. And I created a table of values, the exact same values that we had. So if we click on these, we can see that each of these values does pop up as expected. And again, to the 0 power here, you're going to have a y-intercept right at 1. And you'll notice that as the x's get bigger, going down this way, the exponential graph gets steeper and steeper, and it gets steep really fast. Now we do want to talk about domain and range. Now domain is how far to the right or how far to the left you can go. Well, there doesn't seem to be any limitation on right or left for the domain. So we say that domain is all real numbers, or we could say it is from negative infinity through positive infinity. Now the range is a little bit more difficult to explain. You'll see these negative exponents. That's as the x's go to the left, what's happened to our y's. Y's on the right hand side we can see are going to go infinitely up. But as we go left on our domain, our negative values of x, we can see that the y values are getting smaller and smaller and smaller, but how small do they reach? If we take a closer look here by zooming in, we can see there's actually a little bit of space in between this line and the x-axis. So as our x values go smaller and smaller negatives, we simply get the reciprocal of the larger numbers here. For example, if we were to put 10 for x, we have an output of 1024. If we were to put negative 10, it would be the reciprocal of that number, 1 over 1024. Of course, the calculator went ahead and converted this to scientific notation, but it's really this number, 1024, on the bottom of your denominator, so it would be 1 over 1024. So it doesn't matter how big the x values get or how small the x values get, your y values will never go negative. In fact, there's no way to make them even equal 0. So almost all of our exponential function graphs will have a range that approach 0 but never actually get to 0. So we would define the range as all y's greater than 0 We do not want to put an equal to sign there because our function never actually equals 0. It gets infinitely small but never actually equals 0. Okay, for the next demonstration, I'm going to show you another graph here, which is, you can see, is exactly the same. We got function f, function h. And what we want to point out here is that on this function f, when you put a 0 in for x, you get a 1 for y. You get 2 to the 0 power is 1. And of course we have a 1 right here, and that's usually our starting point. So if I have 1 times 1, I have an intercept of 1. What would happen if I were to change this to a 2? Even though I would get a 2 to the 0 power is 1, I have a 1 times 2, which gives me an output of 2. So if I turn this one on, you can see how the graph changed. So it went from 0, 1 to 0, 2. So the base number here didn't change. So we still have the same steepness or climb in our graph as the other one. The only difference is we have a y-intercept of 2 instead of a y-intercept of 1. So if you were to work backwards from a graph and writing the equation of a function from the graph, one of the indicators that you have a number out here in front that is not 1 would be that you don't have a y-intercept of positive 1, you have something else. In this case 2. So if I put a 3 here, you'll see it goes up to 3 or 4. Now it's still growing at the same rate, it's just now we're starting at 4 and moving up. For this example, we already have a graph shown and a few points, and those points are 0, 2, 1, 6, 2, 18, and you can see that we go on x's 1, 0, 1, 2. We're going by ones. And ideally what we want to do here to be able to write an equation for this would be to create a table of values, which we already have some values there. We just want to list them. So what we have is 0, 2, and 1, 6, and 2, 18. The first thing we want to observe is notice how these numbers go up by 1. If you have an exponential, your numbers on the output side will go up by what's known as a common ratio. And the way you figure out that common ratio is you take a number, like this one right here, 6, and you divide it by the previous number, 2. So 6 divided by 2 gives a times 3 as we go from 2 to 6. And we do the same thing with the 18. Take 18 divided by its previous y. 18 divided by 3 will give you, or 18 divided by 6 will give you 3 again. And it turns out this common ratio is our b value. So in our form where we have y equals a times b to the x, we know that the b value is going to be 3. What we need to figure out now is what is the a value. What does a equal? That goes back to the y-intercept. Anytime I input is 0 for x, we should always output a 1. So this graph should have gone right here through the 1. But you can see it went through here at 2. So if we were to input 3 in place of b, and we put a 0 there, and we put a 2 here because that's the y, 3 to the 0 power equals 1. 1 times a equals 2, therefore a equals 2. So essentially your a value is going to be whatever your intercept is until we start adding translations or vertical or horizontal shifts. So the equation for this one would be y equals 2 times our base number, or our common ratio was 3 raised to the x power.